So, I'm going to talk about the Delfi-Twins mission. You've heard a little bit about it. We came here 1 year ago to present it, kind of to bring you on a path on Memory Avenue. This was exactly 1 year ago. Well, in September 2024, we get the idea. We start, we go. We want to do science. Can we do science with such a satellite? 1 year later, we come here, we present it. This is the idea. This is how we're going to do science. Well, March 2026, we might actually have a bit of a problem. It gets complicated. So, of course, it's nice to always give you a nice picture of everything that works well. Not always. So that's where I'm going to show you something. I don't know exactly when we're going to get to space. So this is an interesting thing. But I want to show you the progress. Let me see. Nope. We built Delfi-PQ. It was a 3P pocket cube. The mandate we got from our department at the University of Delft was, you did one satellite 3 times. Now do something more difficult. And that's why we stepped up. We go for 2. But how do we deploy them? Well, we will actually deploy them attached. I like Tom mentioning the 6 Ps. We actually tried. So these 2 satellites will be deployed attached to each other. There is a rigid mechanism. And after a while, we start to deploy the antennas. Now we have 2 independent satellites hooked up together. They fly as one object, but they should be able to communicate independently. This is our way to actually check out the system. Now, the complicated part. Actually, the science we want to do is related to drag, density of the atmosphere. So we need to increase drag because these things are not big enough to be measurable. So from that point of view, we have now wings. On one side, the first set of wings. Now, another bit, second set of wings. The 2 satellites now are completely deployed. This is actually something like 60 centimeters long, so I think it's going to be trackable by a radar. That's also part of the experiment that we want to do, in which we show that the satellite kind of is small, big, and then becomes again small to actually prove the different tracking performances. But at this point, this is where the dance begins, because we want to split them. And now they're going to go by themselves. Since we have drag control, we have the possibility to actually control the relative velocity between the 2 satellites. And what we want to do is get them to come closer and farther so that we can build and establish a formation, ideally demonstrating autonomous formation in space. This is the main goal we have. Well, actually, again, Memory Avenue. I'm bringing you back to exactly 1 year ago, something you might find out. Well, there is a possible change in regulations, or actually, for now they're still called policies. It's not a real regulation yet. But the policy might become compulsory. Imagine if you signed yourself the Zero Debris Charter from 𝗖cie. Why would you do that? Imagine your national agency says, this is a nice thing to do, so do it. Well, we thought this was a bit of an hypothetical case. 1 year later, actually I'm here, and that case materialized exactly 2 weeks ago. And one more problem. What if you actually do formation flying? Then you get into one of the complicated aspects of these new regulations for debris. Again, I'm not against debris regulations, but you need to be prepared because it's a lot of work. So we're kind of drowning in proving that 2 satellites flying to space will not hit each other, even if they fly somewhere between few tens of kilometers to about 100 kilometers to each other. And it's not that easy to prove it. Also, one of the problems is the regulation is changing. So also national agencies that basically have oversight on your mission, they also find themselves in this kind of moving environment. How do they ensure they meet these requirements? How do they do these things? So national procedures are also changing. And that also adds a little bit to the complexity. But, well, okay, enough for the boring stuff. No, actually, sorry, I forgot one thing. This is the most important one. This is kind of the big problem that we actually have. The moment you have satellites in low Earth orbit, you have to demonstrate what 𝗖cie calls recurrent maneuver capability, which is important. In case you are about to hit, well, the satellite doing the formation with you or any other object, you need to be able to dodge that collision. And if you look in there, actually the next slide, they even require, well, what they require is that you are able to dodge it with a message, with a warning of only 12 hours in advance. So from the moment you receive the warning, within 12 hours, you have to have completed the evasive maneuver because the collision otherwise would happen. And this is a very complicated problem, especially because we always thought this formation to be controlled only by drag. So this is one of the large issues that we're actually finding right now. But okay, I hope now I'm done with the boring parts. Yes. Well, yes, we are having a lot of troubles. The regulatory environment changed around us, but also the team has done a lot of work. So let me show you something interesting. The main thing we want to do, as I said, is formation flying. So we want basically to have two satellites getting farther and closer from each other. Farther as in about 100 kilometers distance maximum, minimum somewhere around 5-10 kilometers ideally. This we can do roughly with a delta V of 20 centimeters per second, which seems easy to achieve. It would make operations easy, because then we would have a weekly schedule for operations. It's nice, especially in university, where you don't want to have people on call 24/7. But in order to do that, we need that the two satellites that are still attached together, they separate, but they have to separate in a well-known direction. Well, well-known means within a cone of about 47 degrees with respect to the direction of motion. If we separate within that cone, so with the satellite pointing within that cone, what happens is that the two orbits vary mostly because of the along track component. This basically means one satellite is ahead of the other one. But they also drift a little bit in inclination or in eccentricity. This basically means the two satellites will cyclically come back and meet each other or collide. But if you actually deploy within that cone, the along track separation is actually large enough to guarantee a safe operations over the long term, also in case of drift. But yeah, proving it in all the possible edge cases, this is actually the complicated bit right now. So now you know a little bit about what the mission wants to do. Actually, we designed everything for a delta V of 20 centimeters per second because this is nice for operations. But for dodging a debris, we're talking about 5 to 6 times, actually even more in some cases, extra delta V needed because we need to act quickly. We need to build up 1 or 2 kilometers of spatial separation between us and an eventual debris, and we don't have a lot of time. So this is one of the large problems we're currently dealing with. But one of the problems we have is attitude control. So we also have a team, and now 2 valuable students have been working with us to demonstrate attitude control. I'm happy Tom has had good results. The mission aimed initially to have passive stabilization. The problem is it doesn't really work, passive stabilization alone. We lack momentum dumping. So in the end, we really needed at least B dot. This is the main point that our mission needs, which is already quite simple compared to pointing. And currently, we have the algorithm implemented. We have the validation ongoing, first in simulation and hopefully before the summer also in hardware. So basically in an Helmholtz cage with the satellite basically hanging on a string, and then we will see if the satellite can dump its own rotation speed. Connected to that, in order to control your attitude, you also need to know your attitude. Several people have mentioned the problem that you know your attitude when you are in sunlight, but not in eclipse. This is actually a large problem because you typically rely on the sun. What if we actually rely on Earth as well? This is not an original idea. BME has worked on it. It has already flown. What if you actually look at the Earth itself? Can we find the Earth limb? Can we use the Earth limb to actually know our attitude, or at least reduce our rotational rate? The point is, the Earth limb is always visible as long as you have an infrared camera. So that is actually one important point, but you might not always be looking at the Earth. That's the reason why we need to do sensor fusion with also magnetometers and gyroscopes. And that's where, in validation, you can see the hardware at the top. We did with a robotic arm and a simulated Earth on a beamer. We could get to 3 degrees RMS for in case the sun is visible, but when we only use the Earth at the end of the eclipse, we actually reach 45 degrees 3 sigma. Not a great number, but at least it still fits within our initial cone. So we have now the freedom to separate the two satellites in basically almost any point of the orbit. Some more updates. We now have control over the moving appendages thanks to a group of students that actually designed the mechanical system. We have a rotating wheel that we use to actually limit the deployment of these panels that actually are used to increase drag. So by rotating this wheel by means of a motor, we can actually control the angle. The system has actually been designed, has been manufactured. You'll see some more pictures later. And it actually went on a shaker to actually prove that it would actually survive the launch. The system is controlled by a motor, and it gives us right now about 20 degrees maximum of inclination change for the panels with a resolution which is rather good for our application. But they limited themselves to that. Another problem that we actually have is the fact that we want to split two satellites. So we also have had another group of students working on the separation mechanism, which should guarantee approximately 20 centimeters per second separation velocity. And actually, we did the demonstration. We got 1.2 meters per second in terms of relative velocity. So the two satellites would just fly away too quickly. It's a bit tricky. It's not that easy to make springs which are so small and actually are accurate in terms of constant. So this is also where we need to do some more work. But it's something that motivated the students a lot. They really worked hard to make this demonstration. Some more work that has been going on is about the GNSS receiver. I love the point that Tom raised. We have a full hardware emulator in-house where we could plug RF into a GNSS receiver. We could generate the orbital dynamics and just play it back. What we can do now, thanks to a receiver from Septentrio, and actually thanks to these 3 girls that helped us, we demonstrated approximately 0.5 meter RMS position error over the full orbit. This is a dual frequency receiver, and we hope within a couple of months to be able to test also a triple frequency receiver. The point is, going down to this level of accuracy allows us to measure actually drag, which is the goal of the mission. Tumbling, another problem. If your satellite is tumbling, is your power system capable of actually generating power? A lot of systems use MPPTs, but the MPPTs typically rely on algorithms like perturb and observe. So you perturb the maximum operational point of your solar cell and then try to see if the power increases or decreases. But if your satellite is also moving, well, your whole algorithm is screwed up. And at that point, your power generation is very limited. So we looked into the biggest dependence on the maximum power point of a cell, which is actually temperature. And controlling the power converter based on the solar cell temperature allows us to make a system which is incredibly faster. Well, now was a bit of a crazy test, but we could use a mechanical shutter in front of the cell, and that's what you see in the plot here. The green track shows the maximum power point capable of following a variation in solar input power from 10% to 90% within 30 milliseconds. It's a crazy speed. You're never going to get to that speed with your real satellite, but we are very confident that during the operational lifetime of the mission, even if there is tumbling, we will be able to actually guarantee full power generation. Okay, this is the slide I was looking for before. We talked about the wings. We also need to control the wings. So we now have a prototype. We actually pressed the production button last week. We have a printed circuit board for the system that would control the motor. So we can program now the inclination of these panels, and that allows us now to select the drag that actually the satellite generates extra. And now I also want to show you all the students. So in this presentation, you see a huge team of students. And some more interesting stuff. I love the comment of Loris earlier on batteries. Yes, batteries are a gigantic problem, especially when they're cold. Through the development, we basically found out that a lot of problems in Delfi-PQ came from the battery that was operated at a temperature which was too low. So we needed a system which could operate at much lower temperatures. So why not just ditching batteries altogether? That was the idea. Can we? It turns out last year a set of supercapacitors was released. They have a capacitance which is incredible. They're huge. Each of those blue cylinders, which are like this big, they have a capacitance of 2,000 farad each. So it's huge, the system. So the whole battery has a capacity of 500 milliamp hour, which is only a third of an equivalent battery that you would made out with lithium-ion batteries. But we have 30,000 cycles, charge and discharge. And we almost don't lose much, even if the system goes down to minus 20 degrees Celsius. We lose 30% of the operational capacity, but we still could operate at full current. So this fixes quite a lot of the problems that we have had with Delfi-PQ. And the other issue we had was the lack of characterization of the thermal properties. Again, thermal problems on very small satellites are bad. This is one of the reasons why Delfi-PQ was so cold. This is why the battery became a problem. So from that point of view, we also managed to characterize a lot of the emission parameters within and outside the spacecraft to actually now be able to improve the thermal models. I think with, this was the last one before you fall asleep. Actually, another very important point from Tom, integration of your satellite. If your satellite doesn't fit in the deployer, you don't fit. This actually happened almost a year ago, but the whole assembly was tested here at Alba to make sure that the two satellites, including the separation mechanisms, actually could fit within the deployer. That's an important problem, because from that day on, we literally froze the mechanical design of the satellite, and now we can work on something else. So I think I went over a ton of stuff. I ran a little bit, but these are kind of the problems that we faced. Unfortunately, I don't have a final satellite design. We're quite late, but we hope to catch up now. Thank you very much.